In these videos, I'll introduce a couple foundational concepts for inferential statistics that will allow us to estimate a population mean within a confidence interval from a random sample. Oftentimes, we don't have information about the larger population that we're interested in, so we have to make inference about it from a sample. So some concepts that we will cover include how you can estimate probability from a normal distribution and a t-distribution, the difference between them and how to know which one to use, the relationship between standard deviation and standard error, the law of large numbers and the central limit theorem, and we'll end with how you can actually estimate confidence intervals in both a parametric method and with a non-parametric method. Parametric method being using the standard error, and the non-parametric method being using bootstrap samples. Our data is from Rebecca Warner's textbook, Applied Statistics, the second edition. It's a collection of heart rates from 130 individuals. We'll refer to these data as our population of interest. First, let's calculate the descriptive statistics for all 130 observations and visualize the distribution. Because the data is normally distributed, we can use the normal distribution and infer probabilities from the data. For example, say you have a heart rate of 89 and you're curious how it compares to the broader population. We can calculate a standardized score, here is a z-score, and then compare it to the normal distribution. We subtract the mean from the point estimate, here the score of 89, divide it by the standard deviation, which is 706, and we obtain the z-score of 2.15. So with that z-score, we can then answer questions like, well, how many people in the population have a higher heart rate? We can use the cumulative distribution function and obtain that in R, which is similar to referencing the z-tables in the back of a statistics textbook. We can also work the other way with a quantile function where we say we want to know what score corresponds to the blank percentile. So in this case, we want to say maybe the 98th percentile. And here again, we're using the standardized data with the mean of 0 and the standard deviation of 1. We could find the z-score that corresponds to the 25th percentile. Now, a more common example would be something like a test score with a normal distribution of scores, say like an IQ test, which has a mean of 100 and a standard deviation of 15. So say you score a 90 and are curious how that compares to the broader population. Because IQ scores are normally distributed, we can infer probabilities, percentiles. We could recognize that a score of 90 has a z-score of negative 0.666, which corresponds to the 25th percentile. With the p-norm function in R, which calculates a cumulative distribution function, we can then use that z-score or the raw score, either one. We just have to make sure that we input the correct mean and standard deviation in the formula. We could also work backwards with the quantile function and find the score that corresponds to the 25th percentile, or whatever percentile we're interested in. Now, we could also find the raw score from the z-score. Remember that the z-score is the point estimate minus the mean divided by the standard deviation. The z-score for a heart rate of 89 in our data set is 2.15. And so say you have the z-score of 2.15 and you want to know what is that heart rate that corresponds to it. To calculate the raw score from the z-score, we multiply the z-score times the standard deviation, and then we add the mean. So let's start with the z-score formula. We multiply both sides by the denominator, which cancels out the standard deviation on the right side, and then add the mean to both sides, which gives us the z-score times the standard deviation plus the mean. In this case, 89. A heart rate of 89 in this data set has a z-score of 2.15. So let's create some samples of our data set of varying sizes and compare them to the population. We'll create a sample of size 9, 30, and then half the population with 65. Notice how, as the sample size increases, the distribution approaches normal and the sample mean approaches the population mean. Now that might be intuitive, that as the sample size increases, it increasingly reflects the underlying population. But now let's take the smallest sample with 9 observations and let's create 500 similar samples of size 9 and then let's average their means. Here we find two powerful concepts in inferential statistics, the law of large numbers and the central limit theorem. The law of large numbers states that the average of many individual samples is, with high probability, close to the mean of the underlying distribution. It's a statement about the center of the distribution. The average of individual samples draws close to the mean of that underlying distribution. The central limit theorem states that the distribution of the sample means tends toward the normal distribution as the sample size increases, regardless of the shape of the population distribution. It's a statement about the shape of the distribution. And what's amazing about the central limit theorem is that the shape of the underlying distribution really doesn't matter. Our population of interest, in this case, is normally distributed. But even if it wasn't, if we took random samples of size 30 or more, the means of those samples would be normally distributed. So we have a population of 130 observations, 130 heart rates. We are taking 500 samples of size 9. Now remember that the distribution of one sample of size 9 was not normal, and the mean and the standard deviation were not close to the population mean and standard deviation. But when we take 500 samples and average their means, we see a close approximation of the larger population. Now in reality, we're not taking 500 samples. But what we're doing is we're leveraging the power of these two concepts when we use the standard error of a random sample to calculate confidence intervals and a population mean. The central limit theorem is a bridge between the descriptive statistics of our sampling distribution and the population distribution. It might help to compare the descriptive statistics of each of these samples. We'll write a function that will give us the mean, standard deviation, standard error, and the margin of error, which we'll discuss more in the next video. Take a look at the output here. As the sample size grows, the means tend toward the population mean, and the distributions approach normal. The last sample is the average of our sampling distribution of size 9, which is a close approximation of our population of interest. Okay, so this is a good place to pause for a minute. In this next video, we'll look at how we estimate the population mean within a confidence interval from a random sample using the standard error.